Hi everyone. So last time we discussed two features of the that could be problematic in terms of how the cost function looks like in the parameter space, which are local minima and saddle points. In this video, we discuss another special feature which is called cliffs, and basically it's called this because it represents a cliff or an upward trajectory that's very steep that happens in certain regions of the parameter space, right? So this feature is particularly present or more common in training of recurrent neural networks, which we will discuss in the last section of this course. And basically, recurrent neural networks are networks that involve feedback loops, and they are used to capture temporal correlations, right? So this feedback loop helps to capture long-term temporal dependencies. So by basically capturing the correlation in a sequence, right? So it tries to learn patterns in a sequence of examples, not just independent training examples, right? So why it happens in recurrent neural networks? Because it's typically the case, and it will become clear as we discuss in the last section, recurrent neural networks like gated recurrent units and long short-term memory cells. These networks typically have in its operation and in the calculation of the backpropagation, which is a version of backpropagation called backpropagation through time. And the abbreviation is usually like this, BPTT, which is basically backpropagation through time. That usually involves raising the same parameter to a power, right? So raising the same weight parameter to a certain power. Now, what that does is that it makes sudden changes around the unity value. If the parameter suddenly becomes more than 1, then you get an explosion in the value in the value when you raise the parameter to a power, right? So you get an explosion in the gradient, right? And that basically results in a phenomena called the exploding gradient phenomena. If that parameter becomes less than 1, then you get another opposing phenomena, which is called the vanishing gradient phenomena. Now, these two phenomena can happen without having cliffs, but they are still problematic because vanishing gradient makes the cost function insensitive to the changes in the parameters, so it's difficult to determine the parameter update. It's similar to having a flat region, and an exploding gradient is a problem because it leads to unstable learning because the gradient is very sensitive. Now, cliffs result in something similar to unstable learning. What happens is that as I move gradually down the cliff, so let's say I am in a region at the bottom of the cliff, and I am minimizing. So I have something that looks like this, right? So I'm minimizing gradually the cost function, and then suddenly it goes up, right? So here I'm moving in that direction and gradually minimizing the cost function, and then at this point, the gradient direction will tell me to move to the left, right? So I move small step, and then suddenly I'm here, right? Now, when I'm here, I have a gradient with a very strong direction to go in the opposite side, right? What does it mean, very strong? It means it points in the opposite direction with a very big magnitude, right? So even a small step, even a small learning rate can result in a huge step, right? So I can go somewhere here where the cost function is high, right? So I can undo a lot of steps, right? How to determine during training that this is happening? If you notice that there is a repeating pattern in the training loss as you watch the training loss in different training iterations, then there could very well it's likely that there is a cliff phenomena happening, right? Now this is a very bad problem because it undoes a lot of the progress that you have made already through training, right? So that could slow training or even make it get stuck in loops, this cliff phenomena. And basically, the current solution to this phenomena is to do something called gradient clipping. And gradient clipping is the following. Even if I fix the learning rate, the problem of the cliffs can still happen, right? Because the gradient magnitude can become large. And what gradient clipping does is that it puts a threshold on the gradient magnitude in the step that I'm making, right? So if so I normalize the gradient magnitude. If it's bigger than a certain threshold, right, then I bring it back to the threshold. And what that does is that it limits the size of the step that I'm taking, right? So that if I go back here, I go back only a little bit. Even though the gradient magnitude is large, I go back a little bit, right? And that's basically it. But that could solve the problem of undoing a lot of training iterations, but you could still get stuck in small loops, right? So you need more mechanisms, more than just gradient clipping. And later in this section, we'll discuss adaptive learning grades that can eventually make you get stuck out of these loops. Not only that, but can make you get faster. So you adapt the choice of the learning grade so that if you feel that you are in a well-behaved region of the parameter space, you can speed up the parameter update step. And if you are in a bad region, then you can slow down the parameter update step. Sounds good? Thank you.